to hold.
Yeah. Even weak or?
Sometimes it does, but the problem in particular is you usually get lots of variation. Have you come across heteroscedasticity?
I did when I did econometrics.
Oh, I see. So you've got variations in the variance,
yeah.
and so
like
that violates.
Error is not distributed normally, isn't it, or something like that?
Sorry. Anyway, errors are distributed.
I do not remember anything about heteroscedasticity.
You should ask. It's useful. All right, have a good one. Bye.
Thank you.
Okay, so hello everyone, and I'm really sorry that last week I have to cancel the lecture and seminar. So we basically have we arranged. If you haven't received the emails, emails should come from timetable from the school. That's in week 6 there will be a replacement lecture. So basically, the original lectures is covered in here, and then week 4 lecture in week 5, week 5 lecture is then in week 6, okay, which originally was intended to be a reading week. I'm really sorry about that. And so if you haven't received the information from timetable, so I'll later on make it as an announcement on Moodle as well, okay, with the venue and time. So it will be week 6 Friday, 12 to 2 for the lecture and 2 to 3 for the seminar. But I will make it in the announcement for the exact venue and time, okay? So that's the first thing. And I've also uploaded on Tuesday the exercise 3, okay? So after today's lecture, so you should be able to do all of the exercise. Especially some exercise like question 6, which I hope after we taught the PACF last lecture, you should be able to do that, but you need to think about some of the details, of course. So hopefully in the seminar, so I would be able to help guide you. But for now, let's move back to the lecture. So for the lecture, so last time, remember we talked about in the lecture last time we talked about a lot of things. We talked about the basic building block for all stationary time series. So AR model, MA model, and also the ACF and PACF as a measure for both the AR model and MA model respectively. And why are they designated measures? Because for AR model, the partial ACF actually has a cutoff at lag P for the AR model, versus for the MA model, there is a cutoff at lag Q for the ACF. Okay, so the ACF is more to look at does it look like an MA model? At the same time, PACF is for us to look at if it's like a finite AR model, okay? But AR and MA models, so they are both simple models where either you have a cutoff or you have an exponential decrease for your ACVS or ACF, okay? The autocovariance sequence or the autocorrelation function, okay? So if it's stationary, then you usually have a slow decrease, exponential decrease, okay? At the same time, so there should be other models which is a little bit more complicated than that, okay? And this is exactly what we will be looking at in today's lecture with some new notation as well for okay. Gonna move this. Yes. So the first thing I want to talk about is actually the generalization of AR and MA model. So last time, in last lecture, so we talked about that, but so let me know if you cannot see the screen, okay? So this time, so we will look at the model that is more general than just the MA or AR model. So this is the ARMOR model. And very quickly, to define the ARMOR model, so if your time series XT actually has this equation to govern is dynamic, so XT equals to, again, a constant alpha plus an AR part, which is similar to an AR model, and that also has P terms. P path value of these time series X. At the same time, it's not only epsilon t plot, but number of terms, which is similar to a moving average model. So plus theta 1 epsilon t minus 1 plus up to theta q epsilon t minus q. So your epsilon t here again is a white noise with mean 0 and variance sigma square. So that's the usual given condition. At the same time, to say this is an ARMA PQ model, so similar to AR and MA, so we need to fix the order. That's why phi p and theta q, they are not 0. In order to fix the order. So with all these, then we say xt follows an ARMA model. With order p and q respectively. So this is a very long writing for the ARMA model, and through exercises and later on some examples we will go through in the lecture notes, then you'll see that for stationary ARMA model, so ARMA model certainly is not always stationary. Remember, AR model can be exploding when they for instance, AR1 model, when phi 1 is larger than 1 in magnitude, then what happens? The model explodes, basically. Okay? It's only when phi is less than 1 in absolute value, then it is stationary. Similarly, so ARMA model, it has to satisfy certain conditions so that the model is stationary asymptotically. But before that, before we go on to analyze its stationarity, so we need to introduce some, so to speak, easier notation for the model. So let's introduce the backshift operator. So this operator is a capital B, and what does it do? So it does for any time series xt, so general time series xt, we denote bxt as xt minus 1, and b square xt as you apply b on xt 2 times. So there will be b applied on xt minus 1, that's xt minus 2, etc., etc. Okay? So b cubed of xt is xt minus 3, etc. So with this notation, then we say xt, well, let's make all the x as the subject on one hand side. So let's subtract all the terms involving x on the left hand side in this model. And then on the right hand side, what's left is alpha plus the MA part, which is epsilon t plus theta 1 epsilon t minus 1 plus up to theta q epsilon t minus q. And with this, with the backshift operator, we can actually simplify this model. We actually simplify this to 1 minus phi 1 b minus phi 2 b square up to minus phi p b to the power p. And then this whole operator applied on xt. So is it correct? So 1 times xt is xt, and then b xt is xt minus 1 multiplied with phi 1, and then up to phi p b to the power p applied on xt is xt minus p, so it's phi p xt minus p. That's exactly this term. So it's correct. And then on the right hand side, similarly, we do this. So theta 1b plus all the way up to theta q b to the power q applied on xt. Okay, so some operator on xt equals to alpha plus some operator on epsilon t. And usually people will denote this as a polynomial in B, okay? So this is indeed a p degree polynomial in B. Think of B as some variable that is not time series variable, of course, but in actual fact it's an operator, but it looks like a polynomial, okay? And this polynomial, so people usually call this phi. And on the right hand side, people usually denote this as capital theta with argument b, okay? So, let me put it here, okay. So actually people give definition on these two, they are exactly polynomials actually. So people call this phi z. Now this time it's a polynomial in z. So 1 minus phi 1 z minus phi 2 z square up to phi p z to the power p. People call this the AR characteristic polynomial. Well, it's a fitting name because this polynomial is basically how the AR part of the ARMA model look like. So this is AR. This contains any characteristic from this AR part, and it's a polynomial. So by the same token, theta z equals to 1 plus theta 1 z plus all the way up to theta q z q to the power q. This is the MA characteristic polynomial. Okay. And so in shorthand, people usually write this. So there's phi b as a whole as an operator in B applied on xt equals to alpha plus theta b, again as an operator applied on epsilon t. And your epsilon t is white noise with mean 0 and variance sigma square. Okay. Well, so ultimately, of course, it is very important about the coefficients, but ultimately, what is determining if the system is stationary or not? Well, if you remember what we talk about MA model, any finite MA model is stationary, right? We talked about that in lecture 1, I think, lecture 2. So stationarity actually comes from AR characteristics, certainly. Even AR1 model cannot be always stationary. So you can guess that AR characteristic polynomial contain information about if the whole system is going to be stationary or not. Okay, and that will be correct. But what exactly is the information that contains in AR model that is going to determine its stationarity? So if we need to determine the stationarity of an ARMA PQ model, then we're quoting a certain theorem. And this theorem is in the textbook. by Brockwell and Davis, it's the Bible in time series analysis, basically. So this is a graduate edition, I think, for the theorem. So this is in the suggested reading list. So if you care about the proof of this kind of thing, so you should go and check out those theorems. I'm just giving you the link here. For the purpose of the course, of course, I just need you to realize this theorem and how, in practice, how to determine if a system is stationary or not, okay? So let me quote the theorem first. So given xt, which is an armor PQ model, now this is especially for armor PQ, we say it is weakly stationary. If and only if, so IFF is if and only if is AR characteristic polynomial. So let me write abbreviation, AR characteristic polynomial, which is capital phi Z, has all roots. Now I'm talking about all roots. Outside of the unit circle on a complex plane. So what I'm talking about, what complex plane? Well, you know, you're given, for an AR model, so you're given a p degree polynomial. So by something called fundamental theorem of algebra, linear algebra. So p degree polynomial, how many roots are there exactly? P roots. No matter real or complex, there could be complex roots, but it will give you p roots. And a p degree polynomial. So quadratic polynomial, so you should be able to solve, okay? There could be complex roots, right? A conjugate pair of roots. Or they can be both real, okay? So for third degree polynomial, so you have 3 roots. It can be one is real and then the other 2 complex conjugate, etc., etc. So p degree polynomial here, we should have p roots, no matter they're complex or not. What are complex roots? So this is, I think, one of the instances that the supplementary material is important, right? So what I'm talking about is this complex plane. Hope this is your high school stuff. If you haven't done this, look at the supplementary material, so what complex number is. So complex plane is, so real part of a complex number and an imaginary part of a complex number. Imaginary part is basically the square root of -1, okay? So a unit circle is something like this, okay? So it is indeed a circle on this complex plane, and the unit circle is basically the shaded area. Okay. So if this is 1, this is -1, this is -1, this is 1. So a unit circle. And the equation, the modulus of Z is less than or equal to 1. So this is the equation of a unit circle. On a complex plane, okay? So in the supplementary materials, I should have mentioned about these things. So any complex number is in the form a plus ib, where I is square root of -1, a and b are real constants. And the modulus of z is square root of a squared plus b squared. Okay. So if you have a little bit of geometry, so coordinate geometry, so this indeed is the equation of a squared plus b squared less than or equal to 1, right? This unit circle. So indeed, if any roots of the phi set equals 0, so this should be equals 0, okay? If any roots of phi set equals 0 falls or touch this unit circle, then that means what? That means the whole system is not stationary. It's only the case that all the p roots of this phi set are outside of this unit circle, no matter they're real or complex roots. If they're outside of this unit circle, not even touching the circle, all of them are outside, then this system is weakly stationary, okay? So ultimately, you need to see if the roots are actually less than 1 in modulus. Less than 1 in modulus. So modulus in the complex variable sense. And confusing, so let's see a word example. So let me quickly give you just the AR1 example. Okay. So xt equals to alpha plus phi xt minus 1 plus epsilon t. You remember last lecture, our calculation assumed that AR1 is stationary, right? So let's not assume this. Let's look at its AR characteristic polynomial, which you should practice in calculating. So from here, the left-hand side should be xt minus phi xt minus 1, which is 1 minus phi times b applied on xt. And therefore, phi z equals to 1 minus phi z. That's the AR characteristic polynomial. It's a linear polynomial for an AR1 model. Okay? So the working is xt minus phi xt minus 1 equals to 1 minus phi b applied on xt, right? And so this one is indeed equals to phi b. Okay? So let's look at its roots. So set phi z equals to 0. And it implies what? It implies z equals to 1 over phi, right? Linear polynomial, there's only one root. Right? So therefore, using the previous theorem, so xt is stationary, is weakly stationary. Well, if and only if the modulus of the root. For real number, modulus coincide with absolute value. So this modulus is basically an extension of absolute value. Absolute value only applies in real number, but for complex number, the general measure is the modulus of a complex number. So this modulus of the root basically is the absolute value of this real root, 1 over phi, is larger than 1. It has to be outside the unit circle. Therefore, the modulus of the root has to be larger than 1 in order that it is stationary. The root has to be larger than 1. All roots have to be larger than 1 for stationarity. And what does that mean? It means phi is less than 1 in magnitude. Okay? And this is exactly the condition that we derived, right? From last time when we calculate asymptotic variance, etc. Okay? So variance is sigma squared divided by 1 minus phi squared. Variance has to be larger than 0. and has to be finite, so it cannot be 1, it cannot be plus or minus 1, at the same time it cannot be larger than 1, because then the stationary variance will be negative. So indeed, it coincides with that. Okay, so remember, variant of xt is sigma squared for an AR1 model, right? Oh, sorry. So okay, the theorem actually coincides with that. Okay, so we agree at least for this situation. And if you encounter an AR2 model, that things become interesting. So it can be real roots, or both can be complex. So for complex roots, you need to calculate the modulus. Okay, so you need to make sure the modulus of the roots are larger than 1 to be, for the AR2 to be stationary, and so on. So you will encounter this as exercises, don't worry. But the important take-home message is, when your xt is a stationary MA model, armor model, then being stationary means the inverse operator exists. Inverse operator exists. So mathematically, when we say stationarity of the model, it means for an armor model at least, so phi inverse exists. So AR operator can be inverted. That means what? That means phi inverse of B, when applied on phi B, it becomes the identity operator, okay? Identity operator means it apply on anything, it's the thing itself. That's identity operator. So, still very confusing. Well, for phi B of xt equals to alpha plus theta B of epsilon t. Now for this armor model, stationarity means your xt can actually be written like this. So applied phi inverse B on both sides. And because the stationary phi inverse exists, plus theta B applied on epsilon t. So it equals to phi inverse of B applied on alpha, which is a constant itself, and then plus phi inverse of B applied on theta B epsilon t. And in general, what is this? This is an MA infinity model. So in an infinite order MA, so epsilon t minus 1, all the way up to epsilon t minus infinity. So for an armor model, if we stay stationary, that means you have an inverse operator exists. At the same time, so xt can be written as an MA infinity model, okay? So these are all equivalent concepts, mathematically, okay? For saying something is stationary. So it's not very solid, so let's look at some really solid example here. So we were talking about an AR1 model, right? With the characteristic polynomial, AR characteristic being 1 minus phi z. So it's 1 minus phi b, apply on xt equals to alpha, plus just epsilon t. So the MA is just trivial epsilon t. If phi is less than 1, which we worked from the theorem, so phi is less than 1, then the inverse operator of the AR characteristic operator exists. But how to exactly calculate this? In particular, what I said MA infinity model, right? So how exactly to express xt as an MA infinity? Well, first of all, the inverse operator exists, as I said. So this inverse operator applied on alpha plus epsilon t. And this equals to 1 minus phi b inverse applied on alpha plus 1 minus phi b inverse applied on epsilon t. So how to write this as an MA infinity model? Well, it turns out that the Taylor's expansion of this, treating it as if it is a polynomial, it will work. So it's the inverse of 1 minus x, where x is less than 1, let's say. Then Taylor's expansion will say this 1 minus x inverse is what? 1 plus x squared up to infinity, right? So it's basically a geometric series. And it applies here as well. So 1 minus phi b inverse, it turns out mathematically, it can be written as sum of phi b to the power j, where j is from 0 to infinity. So we are exactly using 1 minus x inverse equals to sum of xj, j from 0 to infinity. And then applied on alpha, the same for the epsilon t. So for your reference, so 1 minus x inverse equals to sum of x to j, right? For x is less than 1 here. It's basically very similar here. So for x less than 1, this inverse can be expanded like this as an infinite sum. Well, x less than 1 is basically in parallel to the roots of characteristic polynomial is larger than 1 in modulus. Okay? So I hope you can see the connection here. So because phi is less than 1, therefore the roots of this polynomial is larger than 1 in modulus. But phi is less than 1, okay, so you can treat b as something that don't carry any value. So absolute value of phi b will be less than 1, okay? But of course, mathematically, it's not seen like this, okay? So you may ask, okay, this is an operator, so how do we prove this, okay? So, well, the proof is basically just by expansion. So manual expansion, okay? So you can manually iterate this series and then compare to how we expand this using this series. In the end, it's the same. And therefore, this operator inverse is as if we do Taylor's expansion on this inverse polynomial. Okay? So it equals to what? Now, phi to the power j and then b to the power j applied on alpha. Alpha is a constant, so no matter how you backward shift alpha, it's still alpha. And by the same token, so it's phi to the power j. Now, b to the power j apply on epsilon t, that's epsilon t minus j. And you can write better, what is this constant? So sum of phi to the power j, phi is less than 1, remember, in magnitude. So this geometric series work. And it equals to 1 over 1 minus phi, right? So it's alpha divided by 1 minus phi. And then plus the sum of phi to the power j epsilon t minus j. Now this is the MA infinity. So this is the MA infinity model with a coefficient phi to the power j. And what is alpha over 1 minus phi? So this is exactly the expectation of xt. So you can calculate that. So in lecture 2, I think you calculate the expectation by taking expectation on AR1 on both sides. And then expectation of xt equals to expectation of xt minus 1. And therefore, in the end, you get this expectation of xt. Here, you actually directly write xt in the form of the mean of xt plus an MA infinity model which has 0 mean. Okay? So, that's one word example. Well, that's something. Let me introduce another concept first before I go to more word example. Let me know if you have any questions. Okay, so this could be some new concept for some of you. Okay. So let me introduce another parallel concept first, called invertibility. Now, what is invertibility? Well, quickly, if your time series xt is an ARMA model, and this ARMA model has MA characteristic polynomial. So instead of the AR, we now concern with the MA characteristic. Then your XT here is invertible if and only if, again, all roots of theta set equals 0 are outside the unit circle, okay? That is, all the roots are having modulus larger than 1. Okay, that's what it means. Okay, maybe I'll write it down. Okay, that is, all roots are having modulus larger than 1. So that's what it means by all roots outside the unit circle. And with this, so epsilon t will equals to theta inverse of b. So invertibility means theta has an inverse operator. So if we applied it on both sides of the model, of the ARMA model, so theta inverse equals to phi b of xt minus alpha. So let me remind you, invertibility here means theta inverse exists. And then we can simplify this to minus theta inverse of b alpha, and then plus theta inverse of b phi b of xt. So as in ARMA model, if it's stationary, then it can be expressed as an MA infinity. If it's invertible, then it can be expressed as an AR infinity model. So this is the AR infinity part. It's as if it's an AR model, but P is infinite. Okay, the order P is infinite. So it's an AR infinity model. So very quickly, if we consider this MA model, this equals to and so with this particular MA model, therefore you can say theta is equals to 1 plus theta z, right? That's the MA characteristic polynomial. So again, it's a linear polynomial. And what is this root? So hence invertibility. If and only if. The roots, what are the roots? So the roots of phi z, theta z equals 0 is minus 1 divided by theta, right? So the modulus of the roots, minus 1 divided by theta, is larger than 1 in magnitude. For invertibility, that means what? That means theta is less than 1 in magnitude. So again, if theta is less than 1 in magnitude, then your epsilon t is invertible. And epsilon t can be expressed like this for this particular MA1 model. And verify the calculation. So 1 plus theta b inverse applied on minus alpha. That will be minus alpha divided by 1 plus theta. And then plus sum of minus theta b to the power j. So minus theta to the power j. B to the power j applied on xt. That's xt minus j. Okay. So I speed up the calculation already. Okay. And you should, through exercises, so you should be a little bit more familiar with these. So this concept, well, what's the use of that? So, what's the use of this invertibility? Well, invertible time series means all the noise terms, epsilon t, can be expressed as past data. As function, linear function actually, of past data. Which means that potential forecast, so we'll talk about that, forecast can be dependent on past data only. So when we talk about forecasting, so it can be that the forecast equation actually has a certain epsilon t in your model. So if this is the case, then how do you actually put values on the epsilon t? You do not observe that. These are noise terms in your model. So how do you estimate this epsilon t? Well, this epsilon t is for invertible model at least, so this can be expressed back in the original observed data xt. Okay, so that's one of the purpose for seeing if the model is invertible. Okay, So it will be better for your forecasting. Okay. Any questions so far? So I think I've gone through a lot of these different materials. Okay. So, yes.
When you proved that the AR model was stationary if phi is less than 1,
Yeah.
in the previous time we proved that, we assumed that the series was running with like infinite path.
Yes, yes.
Do we assume that here, or can we drop that assumption?
We have to assume that it is running from an infinite past,
Okay.
which I'm going to actually show. That's a good question. Yeah. I'm going to show you if you have a finite path, what does it mean? Okay.
So the AR model isn't truly stationary; it just behaves like one.
Yes.
With infinite
When
path.
you have one for a long time. Okay.
Okay.
Yeah. So yeah, I'm going to demonstrate that. This is also in your lecture notes, but let me very quickly capture the main concepts about how do we see AR model as truly only asymptotically stationary. Okay. So let's put a starting value x minus m equals to a certain constant a. Okay. So if we do this, then rather than writing your xt as an ma infinity, so if you assume phi is less than 1, xt is an ma infinity, so xt is basically sum of phi j, phi to the power j epsilon t minus j. Well, that sum is from 0 to infinity, but here you cannot go to infinity because there's a starting point here. So what to do? Well, we iterate this a little bit number of times and see what happens, okay? So xt minus 1 using the same model equals to alpha plus phi xt minus 2 plus epsilon t minus 1. So let's collect the constant terms and then collect the x terms and then collect the epsilon terms quickly. So if you do not see that, well, let's quickly iterate another time. So xt minus 2 equals what? According to the model, it's alpha plus phi xt minus 3 plus epsilon t minus 2. And then plus phi epsilon t minus 1 plus epsilon t. Then again collect all the constant terms, well, alpha plus phi alpha plus phi square alpha. And then plus the x term, phi to the power 3, xt minus 3. And then plus epsilon t plus phi epsilon t minus 1 plus phi square epsilon t minus 2. Okay, so that will be easier now. So if we run this many times until this term here goes to x minus m. So how many times do we exactly iterate this? Okay, so this observation will help you. So look at the exponent of this phi to the power 3 xt minus 3. Okay, so this exponent is the same as the time being subtracted by here, t minus 3. So t minus what equals to minus m? T minus t plus m, right? So if we iterate it, the exponent here should be t plus m. They always sum to t. So 3 plus t minus 3 is t. Here 2 plus t minus 2 equals to t. And as we iterate it, many times up to x minus m, the sum should also be equals to t. So this exponent has to be phi to the t plus m. How about other terms? Okay. If we iterate it until phi to the t plus m, then here, well, at least we know this has to be phi to the power j times alpha. We know j starts from 0, but up to what? Well, here you can see that if the exponent here is 3, then it's up to power 2. Here exponents, we're adding, we are up to t plus m now, so it should be added up to t plus m minus 1. The same here. J from 0 to t plus m minus 1. You can see it here, so it's up to phi square epsilon t minus 2. When the x term has exponent phi to the power 3. So when the x term has exponent phi to the t plus m, the sum of here is up to t plus m minus 1. Okay? So it's phi to the power j epsilon t minus j. J from 0 to t plus m minus 1. Okay? So according to the initial condition, so this equals to A, and this equals to what? This equals to alpha times 1 minus phi to the power t plus m divided by 1 minus phi, right? I don't care if phi is larger than 1 or smaller than 1, so this is a sum of geometric series, finite sum. Finite number of terms. How many terms are there? T plus m terms. So 1 minus phi to the number of terms divided by 1 minus phi. That's the formula, right? For geometric series. And then plus a times phi to the t plus m. And then plus the ma part, okay? So this ma part, I don't have anything to simplify. That's it. So your xt can be written explicitly in terms of, unfortunately, a function of t. Yeah? When you take expectation of xt equals what? E equals to something dependent on t. Okay? So that is expectation of xt, which is time dependent. Right? And so, strictly speaking, this cannot be stationary, right? Not stationary. So what were we talking about? When we say phi less than 1 is stationary, well, it means asymptotic sense, okay? It means this time series has been gone on for a long time, okay? So, with this setup, infinite past here means m goes to infinity, okay? X minus m equals to a, so as m goes to infinity, we are starting the time series at an infinite past. If m goes to infinity, at the same time phi is less than 1, then the first term will goes to, so it approaches, I should say approach, alpha divided by 1 minus phi, and then plus phi is less than 1, so m goes to infinity, this term is going to 0. Perfect. And then the rest of it is j from 0 to infinity now. Phi to the power j epsilon t minus j. And this is exactly the process, the MA infinity process that we get from our previous example when we say MA1, when we say AR1 is stationary, right? AR1 is stationary. Let's express this as MA infinity. This is the MA infinity, right? But this time we get it from assuming a finite past and then extend it to infinite past. So the story from this calculation, so the process is asymptotically stationary. For phi less than 1, okay? Okay, I think there's enough materials so for you to ponder on. So for now, let me give you a 6 minutes break. Okay, so please come back to 06, and then we will continue.
Okay, well, see you later.
Yeah, that's how I describe it. That's how it should be. Michigan.
Washington should be described as
Yeah, Canada. I think it's just built here.
I think we should be somewhere in America. US.
You know what a great name to say to us? East Grace.
It's like a big business. Definitely big business. Even with the Bulgarians. The Bulgarians, the Greeks. Everybody's just very.
They're very
The
touchy.
whole region's very touchy.
Yeah, because they got.
I wonder.
They got Ottoman
Yes.
Wonder why.
for many years.
Perhaps it's loses, what can I say? Mrs. Baker.
But if you didn't have them, you would have their propolis intact. So.
Is it not intact? I think you.
It's a lot of assets, right? That's a weird.
The church listed as a. You hear ammunition depots? You can just go to other parts of like in Italy. There's a thousand like it's like a billion of those types of temples in Italy.
Yeah, but I mean, it was like a wooden roof.
They should have thought ahead.
Can you guys explain to me why this is the case? Like, why do all rules need to bounce with?
We don't know.
Do you think we know?
I think we do.
Honestly, I think it's quite obvious.
Very
it's
true.
true.
That's why I'm not practice.
Exercise that clarity up.
Hey. Sorry, can I ask you something? Sure. Why exactly do we need the rules to be outside of the circuit station? I'm interested to know.
And as you can see in the AR1 model,
Mm-hmm.
let me show you. So the AR1 model, you can see that here. It's just an illustration, so you can see that in this AR1 model.
Mm-hmm.
So when we do this Taylor's expansion, so it becomes some defined power J.
Mm-hmm.
So you can see that if this phi is actually larger than 1, then the whole thing explodes, basically.
Mm-hmm.
Okay.
Yes.
Yeah. So it's so this is an illustration for
Mm-hmm.
the. This is basically the inverse of the root. Okay. So we need inverse of the root to be less than 1, basically, in order this part about J is.
It's not as
No,
well,
no.
it's not going away.
Yeah, exactly. So in a broader sense, then we need those roots from the characteristic polynomial to be larger than 1 so that
In
In
the
the
AI model,
expansion.
it doesn't go.
yeah, in
into-
all of these powers won't explode. Basically,
Okay.
it's exactly this. Yeah.
So that the infinite series converges.
Yeah, exactly.
Okay. Makes sense.
And the same thing for
For the
convertibility,
yeah.
because there we're looking at the MA model, right?
Yeah.
Because up here we do AR.
Yeah.
And up down here we do MA.
Exactly.
And then it's like the same orientation
Yes.
for the other
Yes.
part. Okay,
Yes.
good,
Yeah.
thank you.
Good.
Thank you guys.
This one. And this is just to illustrate, but it's like the general concept. So when we look at the stationary, we look at the general concept. And this is how you expand the area. And if this was above one, then the sun would just.
Oh, yeah, exactly.
It would, yeah, it would converge. So that's what we need here, and then for, that's just for stationary, we would just get the MA part, the armor model, so it's like the same thing, just. Pretty cool. The other guy, because I switched to one, sorry. The other guy.
It's bad,
Did I show you the movie?
yeah. Like, what is she doing?
Because he made me something, so I was like,
Okay, so let's get back to the lecture. Well, you can see that I've just plotted a graph which appear in your lecture notes as well on page 39. Now, page 39 is actually an ARMA model, so we can look at the model, which is on page, this is example 2.34. This is on page 38, okay? So the model is actually, well, it's a little bit different notation. So let's forget the notation now. Let's directly look at what the model is. So in essence, this is an ARMA model, okay? But this ARMA model, well, there's a whole lot of things missing. So xt minus 1, xt minus 2, all the way up to xt minus 11 is missing, okay? So it only depends on xt minus 12. And then it depends on an MA component, okay? So we call this a seasonal Riemann model, which we are going to talk about within this or next lecture, okay? But the equation is simple to understand. So this look like an ARMA model, okay? Now for this ARMA model, we can actually theoretically calculate the ACF and PACF, asking R to do that. So I've put the code here. The main function is actually ARMA ACF and ARMA, this is basically PACF, okay? So ARMA ACF will produce for you the theoretical ACF and the theoretical PACF, okay? So that's the function. If you want PACF, so you just need to add the argument PACF equals true. So when you plot this, so you have defined the model here by specifying phi, okay, all the coefficients for the ARMA model, and then it will calculate the theoretical ACF for you. So this is the theoretical ACF. This is the same as the plot on the note. Okay, so this is the same as the plot here. Figure 11. So I can make it larger here. So very interesting. So you can see that even up to lag 50, well, things still stick out. But the important thing is this is stationary. Okay, so it is still decreasing. And how do you know the model is stationary? Well, this coefficient ultimately is this coefficient that is less than 1 in magnitude. That's the most important thing. So this is ultimately the AR part is just like an AR model. This is like an AR1 model, but there's a lag of 12 here. Okay. Okay, so that's why we call seasonal at lag 12. But more to that later. So 0.8 is less than 1, and so the whole model is stationary. So we should expect ACF and the PACF as well will go to 0 very quickly, exponentially fast. So for the ACF, well, it is going to 0, but it's even up to lag 50 is not very quick, okay, but it's stationary, okay. So if we plot more lag, then you should see that the PACF is actually going to 0. So if we plot here the ACF, I don't know, if we put 100 here, so you can see now I plot 100 lags. So you can see that it is indeed, well, it's going to 0, is exponential. The thing is, it's not quite fast because it's at lag 12, and then the coefficient is 0.8. It's not too much smaller than 1, okay? So the ACF goes to 0 slowly, okay? So sometimes it's positive and then sometimes it's negative, okay? Is to do with the seasonal part. All the coefficient from t-1 to t-11, they're all 0, okay? It's only t-12 that has some coefficient. So it will produce something like that. We'll talk about that later, seasonal Riemann model. At the same time, the PACF also goes to 0. Well, it actually goes to exactly, mostly exactly to 0. Because it's going to 0 so fast, it basically plotting something that is non-existent, okay? And why is it going to 0 so fast? Well, the coefficient now on the MA model part is 0.5, okay? So somehow for the PACF is more to that coefficient. So after certain lag, it basically is so close to 0, so you cannot see it anymore. But theoretically, I think the PACF is never equal to 0 exactly. It's just so small after certain lag. Okay. Just to give you a feel, so this is a general ARMA model, and what does is ACF and also PACF look like? Okay. Any questions? So, if you look at the lecture notes, let me close this. If you go back to the contents, table of content, so you can see that we should be now in this stationarity and invertibility of an ARMA process, which is section 2.9. And then we should be teaching the following materials, but here, let me skip this first, and then we'll come back to it later. Let me skip this and directly go to chapter 3. So after talking about ARMA model, I think it's the high time for talking about how to estimate them, okay? Before we talk too much further about any theoretical analysis of these ARMA model or extension of that in general, okay? So let's talk about if we have data, so how do we estimate this ARMA model, okay? So, and that's what I'm going to do. So we'll start with chapter 3, and then we'll come back to the latter part of chapter 2, which is a seasonal Riemann, so and trend seasonal adjustment, and then the arch and gauge model. We'll come back to that. But for now, it's chapter 3. So let's get to. Okay, good. 10. And in order to talk about estimation of these AR and MA model or ARMA model, if we have data, then we need to talk about something very important. And the sole reason for in the past lecture talking about ACVS and PACF, right? So, and this is exactly because the numerical version of these ACVS and PACF, they are very useful, okay? And so let's talk about the sample ACVS and ACF first. So if XT is stationary, so let's assume it's stationary. If it's stationary, then it has the ACVS, so let's SH, sorry. B is ACVS, the autocovariant sequence. Now, of course, so sample, then you are given data. So for the time series xt, suppose you observe your data x1, x2, all the way up to x capital T. So your sample size is capital T. Then you can estimate your SH by this formula. So I will give you two potential candidate. So one is the sample correlation. So in this, so we are multiplying xt plus h and then xt subtracted by the mean, of course, the x bar. And then divided by t minus h, okay? So we're only summing t minus h number of terms here. So we divide by t minus h. The second term is this shp. So this is 1 over t. So they're basically the same. But, well, the denominator is different. One is t, and the number of terms is t minus h, sorry. So you're summing t minus h terms, but you divide by t. So the first option, you sum t minus h number of terms here, but you divide by the number of terms, t minus h. So which should we choose? Well, I think I talked about that in R, in exercise 1 actually. So in R is always the option 2. Okay? So we will never divide it by the number of terms, okay? So we will divide it by the sample size t. So your question, so why is that? Doesn't divided by number of terms summed here look more unbiased, and that's why it's SH bracket U. U is for unbiasedness, but his bracket P is what P is our preferred version. So everyone preferred this. So why is that? Remember we talked about positive semi-definiteness? So the first option, the unbiased option, is actually not PSD in general. But the preferred version, you can prove that it is actually PSD. Okay, so as you calculate the sample ACVS at higher lag, you're using less number of terms. But you divide by less number of terms as well. So the estimate is actually getting cruder and cruder. In the end, it's not PSD in general. Secondly, your SH should go to 0 as your lag goes to infinity. Remember, we're talking about stationary time series, so the ACVS should actually goes to 0 as you consider higher lag, theoretically. So this is a theoretical result, but the unbiased version actually is not going to 0 as your H is going to infinity. But your preferred version here, bracket P, does go to 0 as H goes to infinity. So there's one final reason, and this final reason is linked to your exercise. So in your exercise 3, if you have seen that, which I upload on Tuesday, so you see that you're looking at some white noise and then you proved the mean square error of the preferred version is actually less than or equal to mean square error for the unbiased version. And in general, this is true, okay? And with these 3 reasons, so we actually anyone doing time series, so they will divide by t rather than divided by t minus h, okay? So this is a little bit different from your sample covariance between 2 variables when you do more fundamental statistics, okay? So for time series context, these 3 are actually more important thing to consider and to conform to. And that's why we prefer the second option. Now this is the ACVS, so that's the formula. Okay. So with data we can estimate that, but how about the ACF? So for ACF, the sample ACF, use this formula, so we'll have equals to the SH divided by S0, which you, in terms of data, is like this, okay? T plus H minus X bar, the next T minus X bar, and then divided by 1 T, XT minus X bar squared. So that's the formula for the sample ACF, okay? And this, by the way, is what we're plotting using R, okay? So remember last time, so we demonstrated some sample ACF, okay? So we plot, we have data, and then we can ask R to plot it, the sample ACF. So the function is just ACF of the data, and then it will show you the formula is exactly this, okay? Okay. Any questions? So it's just definition here, and it will be solved for the next few topics. So we talked about the sample ACF, so let's talk about the sample mean, okay? This we can go through very quickly. So if xt is stationary, with mean equals to mu. So like in the ACF, we estimate mu by x bar, right? X bar equals to 1 over t times the sum of the data. And of course, this is an unbiased estimator, so expectation of x bar. No matter if the variables are correlated or not, sum of the xt, when taken expectation, is the sum of the expectation, right? So if we sum mu divided by t, so t of mu divided by t, which is just mu. So this is unbiased. So x bar is unbiased. For mu, but how about the variance? Well, if you remember, if all the x are actually independent or uncorrelated, then variance of x bar is 1 sigma square over n, right? So you have done this in your first year statistics. But how about in time series context? So let's quickly go through that. So it's the covariance of x bar is covariance of x bar and x bar itself. So let's write that. But using different dummy variables here to avoid confusion of ourselves. So let's use t and s to denote the dummy variable. So then we can take out the 1 over t on both, so 1 over t squared. We can take out the summation as well. And that's why it's important to use 2 different dummy variables for the summation. Therefore, the different x bar. So it's covariance of what's left with is xt and xs. Well, so what is that? So 1 over t squared. Let me write it as one summation, okay? T and s from 1 to capital T. So what is covariance of xt and xs? So in terms of the ACVS, that's s of the distance between t and s, right? Let me change this to a less confusing dummy variable, I and j. So it's I and j from 1 to t as of the distance between I and j. So what is this? Well, if you consider so this is related to how you simplified it. If you consider variance of x1 up to xt, the Topless matrix is actually this, S0 S1 up to st minus 1, and S1 S0, S1 again up to st minus 2, etc., etc. This is up to st minus 1, st minus 2, all the way back to S0. Right? So this is a Topless matrix. Well, Topless matrix means the diagonal contains all the same value. Okay, the main diagonal is S0, off diagonal is S1, etc., etc. It's a symmetric matrix, of course, for the variance matrix. So it's a symmetric Topless matrix. And how is it related to our summation? Well, our summation is exactly summing all the elements in this matrix. Okay? If you look at that, so if I is t, j is 1, then we summate st minus 1. Okay? But we also need to sum s1 minus t as well, which is the same. Okay, so in the matrix there are two of them. That exactly correspond to that. Right now I is t, j is 1, or I is 1, j is t. Okay? Etc. etc. So we're basically summing these elements in this topless matrix. Okay? So how about summing and this summation I and j is basically summing from rows and columns. But how about let's sum it over diagonals instead? After all, its diagonals are the same. Right? Up to the last diagonal, which is just one element, st minus 1. The diagonals have the same element, so why not sum them over diagonals instead? And then this becomes the sum of. So how many diagonals are there? So well, we need to label this diagonal. So the last one is t minus 1. And the most positive one is t minus 1. The most negative one is minus t minus 1. And we are summing t minus h of them. When h is 0, there are t of s0. When h is 1, 1 or minus 1, there are t minus 1 of s1, etc., etc. Okay? So from summing rows and columns becomes summing diagonals. Okay? So this diagonal is minus t minus 1. And then minus t minus 2 and so on up to 0, and then 1, 2, 3, 4, 5 up to t minus 1. Corresponding exactly to how many diagonals? There are exactly 2t minus 1 diagonals, right? Okay, so this simplified to 1 over t times the sum of h from minus t minus 1 to t minus 1 times 1 minus h over t sh. Okay, so I multiply by 1 over t inside this to make it here. Okay, and okay, what do I want to show? Well, I want to show, at least illustrate to you. Sorry about that. I want to at least illustrate to you that variance of x bar, which is, let me write that again, 1 over t sum of the t minus 1 diagonal up to positive t minus 1 diagonal, 1 minus h over t times sh. So with this sum, it will be similar to 1 over t, the sum of h from minus infinity to infinity of sh for very large t, okay. So in these courses, when you say large sample parameter, it means it goes to infinity theoretically, okay. So if it goes to infinity, of course, it's going to be 0 if this sum exists, okay. But this sum usually is the sum that people use to actually simplify the calculation. So this number of terms here is different for sh, but here, when t is large, actually we can assume that the number of terms is the same. Okay. So if xt is given to you or id, then what do you have? You have variance of x bar equals to sigma square over the sample size t, right? And the formula here is 1 over t, the sum of sh. If it's IID, then only S0 exists, right? So, and all other S are 0, so it's S0 divided by t. Okay. So I spend a little bit of time to convince you of variance of x bar. So we use this simplifying function usually. So theoretically, if we know the ACVS, okay, so we use this ACVS to calculate the variance of x bar. Okay, so it's basically sum of them divided by t. Okay, that's for sample is usually approximately true. Okay, so we have expectation and then the variance of x bar. Okay, so with these, so some inferences can be made. Okay, for these parameters, but for inferences, so we only restrict ourselves on the next thing, which we will talk about, the Walker estimator. Before that, any question? So what are Walker estimators? So let me write it down. So the next thing we want to talk about is actually estimator for our AR model. Talk about the general estimation of the stationary mean and what is the variance of this x bar, so sample estimator for the mean. Okay, so we can calculate that as well. Okay, so how about the estimator for a simple AR model, and then later on we'll extend this to the ARMA model. Okay, so this is called Walker estimator for an AR model. So we introduce this because it takes a simple form. First of all, it's a moment estimator. Okay, so if you don't know what moment estimator is, well, we're basically equating population moment, okay, to population moment to the theoretical moment, okay? Population moment to theoretical moment. So you'll see what I mean in a minute. So suppose your data is x1 up to xt. So again, for this AR model, so you have this data, x1 up to xt, and you want to fit the data to a stationary ARP model. So your xt will equals to alpha plus phi 1, xt minus 1 plus up to phi p xt minus p. So what are we doing? We have data x1 up to xt. Okay, so suppose if it follows an ARP model, then what should the ARP parameters be? That's what we are doing. Okay, we are estimating phi 1 up to phi p. If it's going to follow an AR model, what's the best fit? Okay, so to speak. So let's consider its moments. Okay. Let's take covariance with xt minus h on both sides. Where h, the lag, is larger than 0. So what happened is xt and xt minus h, that's sh, right? And then alpha can be ignored, it's a constant, covariance of a constant is 0. Now covariance of phi 1 xt minus 1 and xt minus h, that's phi 1 sh minus 1, yeah? And then plus phi 2 sh minus 2. Covariance of xt minus 2 and xt minus h, distance is h minus 2. And so on and so forth, plus up to phi p as h minus p. Okay, well, that's still one more term. Covariance of epsilon t and xt minus h. So what I've been talking about, in the last lecture, I asked you to assume that this will be 0, right? For stationary xt. For stationary xt, which follows an armor-like model. But why is that? Well, this xt minus h if it's stationary, then we have just learned that it can be expressed as what? As an MA infinity. So some coefficient psi j, I don't know what that is. Oh, t minus h minus j. Okay. So j from 0 to infinity. Something like that. Then what is covariance between xt minus h and epsilon t? This will then be summed from 0 to infinity psi j. I don't know what psi j is, I don't care here, as long as there are some coefficients that the expansion exists. Covariance between epsilon t minus j minus h and epsilon t. Can this covariance ever be non-zero? Covariance between epsilon t minus j minus h and epsilon t? Well, no, they don't overlap. H is larger than 0, j is from 0 to infinity. So this is always 0. So this is indeed 0. As I've taught you to assume first in the last 2 lectures, okay? Covariance between epsilon t and xs, where s is less than t, is 0, okay? So I kind of illustrated to you that this is true because of the MA infinity representation, okay? So this term is 0. Then how do we calculate this phi? Okay, so let's write this set of equation. As we change h, we get different equations. So the first one is S1, let's h equals to 1. So it's phi 1 S0 plus phi 2 S1 plus all the way up to phi P S1 minus P, that's SP minus 1. And then when h is 2, this is phi 1 S1 plus phi 2 S0 plus all the way up to phi P S2 minus P. That's why that's P minus 2. All the way up to, let's consider up to P. And why do we consider up to P? Well, we want P equation, P unknown basically. The phi's are what we want. There are P unknowns, phi 1 up to phi P. So we need P equations to solve that, right? Just phi 1 SP minus 1 plus phi 2 SP minus 2 all the way up to 5p as 0. Okay, and this is equivalent to a certain system. Okay, so it's equivalent to this system S1 up to SP as a factor will equal to a certain matrix, which is S0, S1 up to SP minus 1, and then S1 up to SP minus 1, S1, S0 up to SP minus 2 here. And then this is the last row is SP minus 1, SP minus 2, all the way back to S0. This multiplied by phi 1 up to phi p. Okay? And then we will write it as a gamma p equals to capital gamma p as a matrix times phi, okay? So this factor is gamma p, this matrix is capital gamma p, this factor here, phi 1 up to phi p, is the factor phi here. So phi is what? Phi is capital gamma p inverse times gamma p, okay? So theoretical moment of the data is S1, S2 up to SP. The theoretical covariances, okay, autocovariances for the time series. And these theoretical covariances, yeah, we can match it to the population moment, okay? For this particular model, so the population moment, well, it depends on the phis, okay? In this way, in this linear equation way. And so in the end, we can solve for a factor of phi equals to a function. Well, it's a little bit complicated involving inverse of something, but ultimately it's just a function of theoretical moments, the ACVS. Now, these ACVS can be estimated standardly by our data. Okay, so that's what we call moment estimator. Okay, so this estimator is based on, so we can add a hat here, where all the SP, SJ are replaced by SJ, our preferred version of estimator. Okay, so all these estimators are actually with SJ replaced by the sample version of ACVS. All right. So this is the UWalk estimator and how we developed it, okay? Let me write just a little bit more. So I know it's a lot of materials, this lecture. So we basically, what we do is plug in our preferred estimator from the data for the theoretical moment. It becomes a sample moment, sample ACVS for the theoretical ACVS. And then phi hat can become capital gamma p inverse times gamma p hat. Okay? So your capital gamma p, well, will be done by S0 hat, S1 hat, SP minus 1 hat. So everything become hat, okay? This hat is basically the same as the preferred version of the moment estimator, okay? This gamma p hat is what? Is S1 hat up to SP hat. Is it the end of the story? So for this estimator, for this AR model, if you go back if you go back up to the model itself, there's actually one more parameter that we need to estimate, and that's sigma square. So how do we estimate sigma square? So we estimate all the phi already. Well, let's make another equation, okay? So take covariance, this time with, just xt. On both sides of the ARP model, then S0 equals to phi 1 S1 plus up to phi PSP, and then plus covariance between epsilon t and xt. This one equals to sigma square. I hope you know why this is the case. I basically illustrate to you how to calculate that in last lecture. Okay. Think about this, okay? So now, therefore, sigma square is S0 minus this linear combination. What is this linear combination? Using our notation defined earlier, is phi transpose times gamma p. And therefore, our sigma square hat is what? Is our preferred version of S0 minus phi hat transpose gamma p hat, okay? So that's the Walker estimator for the phi's and the sigma square, okay? So this is the, people call this the Walker equations. So this is the Walker equations, okay? So when people talk about Walker equations, this is the set of equation, okay, for an ARP model. All right. I don't think I have enough time to talk about anything else actually. So let's go back to any questions. So let's go look at the lecture note for last time. So this is basically correspond to the Walker estimator, that's section 3.3. So you can see the derivation is in here. I use the same notation as well. And then there are certain asymptotic results associated with that, but I will talk about that in the next lecture. Okay. So thank you for coming. So I'll see you guys in the next lecture for the seminar. So we will continue in the next hour. Okay.
That's great practice. If you can find instructor back like this, but this is good for your call. Yeah.
So
It's like a
it's sometimes
It's crazy. You have to send a photo.
Well, you can see it, guys.
And you can see.
You'll
the
see like a
straight-
weird girl with pink hair.
I actually saw someone with super thin hair the other day. They were really cool.
I'm telling them that like as soon as long as they keep it natural. I don't want makeup.
Pink hair.
And then also she's like cutting and coloring so it's that's kind of
It's just practice.
no, it's like the competition. She's actually she wants to.
Is it a year long? Oh.
No, it's just once, but then I just paid. You just get free haircuts.
I have to get.
Thanks for supporting me.
That's a good one.
I'll send you their list. Thank you.
I would take my hair with color.
Oh no, I could do the massage as well. If you want.
Which one?
Actually, I think I'll just.